Hello everybody. Um, so we will be looking at random variables, and we will look at discrete random variables, continuous random variables. We will be looking at the uniform distribution and the normal distribution. And the normal distribution will be the next video will be on the uniform distribution, and the video after will be on the normal distribution. Okay, so what's a random variable? A random variable is a variable whose value is a numerical outcome of a random experiment. So basically, when you have a random experiment, there is an associated sample space containing all the outcomes of the experiment. And a random variable, you can think of that as a function from the sample space into the set of real numbers. That is, you assign a number to each of the outcomes in the sample space. Here's an example. If I toss a coin 3 times, and if I then let x to be the number of heads that we obtain, then what are the possible values of x? Well, x could be either 0 or 1, 2 or 3. So if I toss a coin 3 times, notice that we get 8 possible outcomes, and then each outcome has an associated value for x. So for the outcome HHH, the value of x is 3. That remember, x is the number of heads, so the value of x would be 3. For this outcome here, HTH, the value of x would be 2, and the last one, TTT, the value of x would be 0. So again, x is the number of outcomes here. So each outcome has an associated x value. So you can think of x as a function such that it's a function that associates each value in the sample space exactly one real number. And we say that a random variable is discrete if it has a finite number of possible values. And again, the example that we just looked at is an example of a discrete random variable. That is, if I toss a coin 3 times, and if x is the number of heads, then that's a discrete random variable because it has finitely many values. Now, we can express events by using x. So for example, if we write x is equal to 2, then it represents the event of obtaining 2 heads in 3 tosses. So the event x equals to 2 has 3 outcomes in it: HHT, HTH, and THH. So these are the 3 outcomes in the event represented by x is equal to 2. So what if I write x greater than or equal to 2? So if x is greater than or equal to 2, then what event is represented by that? Well, if x is greater than or equal to 2, then you get this outcomes together with the outcome h, h, and h. So there will be 4 outcomes if I instead write x greater than or equal to 2. Here's another example. If I roll a die and let x be the if I roll a die twice and x be the sum of the numbers that face up, then x can take on any values between 2 and 12. We've seen that before, and these are all possible outcomes from the 2 rolls. So there is a total of 36 possible outcomes from rolling a die twice, and we are looking at x to be the sum that we obtain from the two rolls. So for example, when x is 2, so let's say when x is 2, then what is that event when x is 2? Well, that means it's the event of getting a sum of 2. Well, in that event, you only have one outcome, which is one dot in both, getting 1 from both rolls. Right? That's the only way you can get 2. So this is the only outcome in the event x is equal to 2. If the event x is equal to 3, well, the event x is equal to 3 means it's the event of getting a sum of 3. So the only way you can get it is getting a 2 from the first roll and 1 from the second, or 1 from the first and 2 from the second. So these two outcomes here will be in the event represented by x is equal to 2, and so on. The probability distribution of a discrete random variable x lists the values and their probabilities. So I should mention here, I'm talking about a discrete random variable here. So here in the first row we list out the values of the random variable x. In the second row we write down the probability associated with each value of x. So remember, each value of x represents an event, and these are so P1 is the probability of the event represented by the value x1 of x, and so on. And the probabilities here must add up to 1, because the total probability is 1. Another way of thinking about this table is that it represents the probability mass function, or in short we say PMF. So the PMF, or the probability mass function, is this function p of x, which is equal to the probability that capital X is equal to x. So this is the probability that the random variable x takes on the value small x. So remember, x is equal to x, that represents an event, and you're taking the probability of that. So here P1 is basically the PMF function evaluated at x1. P2 is the value of the PMF function when x is equal to x2. Here is an example. Let's say that we have a bottle cap and we toss it 3 times, and x is the number of times the cap drops with the open side up. Suppose on each toss the probability that it drops with the open side up is 0.7. So again, the probability that the open side is up is 0.7 each time we toss the cap. So so notice that if I take, what's the probability that I'm going to get? So U here represents that the open side is up, and so the probability of getting probability that the in three tosses the bottle cap will drop with open side up is the following: P of U, which is probability of U times the probability of U times the probability of U, because these are independent, the tosses are independent, and then each time the probability is 0.7, so if you multiply them you get 0.343. So that's the probability that in all 3 tosses the open side will be up. Now if I toss a bottle cap 3 times, then the sample space will be what? Well, we can use a tree diagram that we have seen before, and then we can list out all the possible outcomes, and we're going to get 8 possible outcomes. So we can get D means the open side is down, U means the open side is up. So we might get the result where in all three tosses, the open side is down. We can also have all three tosses giving us open side up, and then we have these other 6 possibilities. And if I take x to be the number of times the open side is up, then x could be 0, 1, 2, or 3, and then the associated probabilities are given on the second row. So for example, how did I get 0.027? Well, that's the probability that x is 0. Well, the probability that x is 0 means it's the probability that in all three tosses we get in all three tosses the open side is down. So when x is 0, that's the event of getting DDD. Well, what's the probability of getting DDD? Well, that's the same as the probability. How do I find the probability of getting DDD? Well, the probability of getting D. So the probability of getting U is 0.7. So the probability of getting D would be 0.3. So if you multiply 0.3 3 times, so 0.3 times 0.3 times 0.3, you're going to get 0.027. So that's the probability that x is 0. And similarly, on the other hand, the probability of getting probability that x is 3 means that in all three tosses we get u, and so in that case the probability would be 0.343. And you can check the probabilities, the probability of getting 1. So when you get the probability of getting the probability that x is 1, right? That means the open side is up only once out of the 3 tosses. So that is represented by these 3 outcomes, right? So the probability that x is 1, the event x equals to 1 has 3 outcomes here, and the probability of each of these outcomes would be what? Well, the probability of each of these outcomes would be 0.3 times 0.7 and 0.7. So 0.3, 0.7, 0.7. If you 0.3, 0.7, 0.7. If you multiply them, what do you get? Okay, so 0.3, 0.7, 0.7, you get 0.147. And so the probability of each of these outcomes would be 0.147. And then again, I'm using this type of argument, we're using the independence. And then if there are 3 of them, each one has the probability 0.147. So if I add them up, right, sorry, so I'm making a mistake here. So what is the probability of the first one? The probability of the first one would be the u is actually a 0.7, 0.7, and then the probability of D and D would be 0.3 times 0.3. So the probability of the first one would be 0.7 times 0.3 times 0.3, and which is equal to 0.063. And the probability of each of the other 2 will also be 0.063. And then if I add them up, we're going to get 0.189. So that's the probability that x is 1. And the probability that x is 2 would be 0.441. Again, you look at this, x equals to 2 is the event where you have these 3 outcomes. And the probability of the first one would be 0.7, 0.7 times 0.3. And the 0.7 times 0.7 times 0.3, that's 0.147. And then the probability of the other 2 would be the same. And if you add them up, you get 0.441. So the probability of any event is the sum of the probabilities of the values of x that make up that event. If we again look at the example where we are tossing a bottle cap, where x is the number of times the open side is up, then remember that this is the probability mass function, or the probability distribution that we got for this variable. And let's ask, what is the probability that at least 2 times the cap lands with the open side up? Well, to answer that, that means I want the probability that x is larger than or equal to 2. Well, that's the same as the probability that x is equal to 2 plus the probability that x is equal to 3. And that's 0.441 plus 0.343, which is equal to 0.784. So again, the probability of any event is the sum of the probabilities of the values of x that make up that event. What's the probability that the cap lands with open side up fewer than 3 times? Well, in this case, we're asking what's the probability that x is strictly less than 3, which is the same as 1 minus the probability that x is equal to 3. Actually, I should say x is greater than or equal to 3, but x doesn't take values bigger than 3, so it is 1 minus the probability that x is 3, and which is 1 minus the number 0.343, which is 0.6557. So here we are using the idea of complement. So the x equals to 3 is the complement of the event x is strictly less than 3. And so the probability that x is less than 3 is 1 minus the probability that x is 3. All right, so here I have a distribution for a variable, and the question is this a valid probability model? Well, to check that, we have to make sure that all the probabilities are non-negative and they add up to 1, and that's the case. If I add 0.3, 0.3, 0.1, 0.30, we get 1. So this is a valid probability mass function, or this is a valid distribution. Again, the probabilities must be non-negative, and they must add up to 1. Here I have the same distribution as in the previous one. I'm just asking what's the probability that x is 0. Well, that's 0, we can see. And what's the probability that x is less than 4? So x is less than 4, so we add up the probabilities here, here, and here. So that's 0.7. All right, so a continuous random variable x is one where it takes on values in an interval. So x takes on a continuum of values. So for example, pick randomly a number between 0 and 1, then there is an infinity of numbers between 0 and 1. So if I'm picking a number randomly between 0 and 1, so then x could be any value between 0 and 1. So that's going to be a continuous random variable. Now, continuous random variable, in that case, how do we assign probabilities? Well, when you have a continuous random variable, the probability of a single outcome is 0, and so for example, let's say that let's say that we are studying the height of a population, and so then x here, x is a continuous random variable because the height can take on any value, any non-negative real number, so height can take on any positive real number. So in that case, the probability of a single outcome is going to be, so if I say what's the probability that x is equal to 2, in that case will be 0. So you might say, well, that's kind of counterintuitive. Well, you see, when we talk about height, because of the lack of precisions and all that, it is more appropriate to say that the height is between 6.27 and 6.28, right, or something else. So the probability of a single outcome is 0. We use the probability density function. So remember, in the case of discrete random variable, we use the probability mass function. The analog of that here would be the probability density function, the PDF, but here the PDF function is the rate of probability per unit of x. So f of x represents the rate of probability per unit of x. The graph of the PDF is called the density curve for x. The graph of the PDF is called the density curve for x. The probability of any event is the area under the density curve for the values of x that make up the event. Only intervals can have non-zero probability, represented by the area under the density curve for that interval. The area under the entire density curve equals the total probability, and so it is equal to 1. So let's say that we have the blue curve here is the density curve for a continuous random variable. So in this case, the probability and area under the, so in this case, what is the probability that the variable is between small x1 and x2 is the shaded area under the curve here. So this shaded area is the probability that x is between x1 and x2. So you can see that the probability that x, because the probabilities are given by areas below the curve, the probability that x is equal to a particular value will be 0, because the area would be 0 in that case. So the probability that x is between x1 and x2, that is the shaded area under a density curve, is the proportion or percentage of individuals in a population with values of x between x1 and x2. So here's what I mean by that. Again, think of x as let's say we are studying the height of a population, and so x represents height, let's say. Then the shaded area here, which is the probability that x is between x1 and x2, means the proportion or percentage of individuals in the population for whom the height is between x1 and x2. So again, the shaded area is the percentage of individuals in the population having a height between x1 and x2. So here is an example of a continuous random variable. So if I have a random variable x that has the following density curve. So if we say that x is uniformly distributed over the interval from 0 to 1, if its density curve is given by the following function. The f of x is 1 if x is between 0 and 1, and the value of f of x is 0 otherwise. So you can see that when x is between 0 and 1, the value of the function is 1. So this horizontal line here is the density curve here. and the area under this density curve is exactly 1. And you might say, well, what kind of variables will have uniform distribution? Well, if I am randomly picking a number between 0 and 1 and taking that as a value of x, then that x has a uniform distribution like this. And another example would be, let's say that you are, let's say that x is the waiting time for a waiting time. So let's say you are standing at a bus station or a bus, for a bus route. You're waiting somewhere at one of the booths for buses. So if you're waiting there, then your waiting time could be uniformly distributed. The probability that x falls between 0.3 and 0.7 is the area under the density curve. So the probability that x is between 0.3 and 0.7 would be equal to the area here. Well, the area would be basically the area of a rectangle, which is length times width, and the width is 0.4 and the height here is 1, so it'll be 0.4. Now, when you have a uniformly distributed variable, the probability, for example here, the probability that x is bigger than 1 would be 0, because outside when x is bigger than 1, the value of the PDF is 0. So when x is bigger than 1, so we have the interval from 0 to 1, right? So the probability of x over any other interval, outside of the 0 to 1 is going to be 0. The probability of a single event is 0. So the probability that x is 1 would be 0. So again, let's say I have the uniform distribution over the interval from 0 to 1. And let's find a couple of probabilities. So the probability that x is between 0 and 0.5 is equal to the width. So 0 and 0.5, that's going to be the width times the height here. Height is always 1, so it's going to be the same as the width, and 0.5. Now notice that the probability that x is between 0 and 1, where the inequalities are strict inequalities, we still have that the probability is 0.5. That is, the probability of an interval is the same whether the boundary values are included or excluded. The probability that x is greater than or equal to 0 but strictly less than 0.5 is still the same. What's the probability that x is less than 0.5 or x is greater than 0.8? So if I ask, what's the probability that x is less than 0.5 or x is greater than 0.8? Well, these two events are disjoint, so you can find them by adding. So probability that x is less than 0.5 plus the probability that x is greater than 0.8, which we can also say it's 1 minus the probability that x is between 0.5 and 0.8, and which is going to be 0.7 at the end. All right, here's another example of a density curve. So if let's say that we randomly pick two numbers between 0 and 1, and y is the sum of the two numbers. So in that case, y can take on any value between 0 and 2. And the density curve for y turns out to be this following curve, which is a triangular shape. So the density curve here is this. The density curve here consists of these two line segments here. The height of this point here is 1, and the area below the area of this triangle is exactly 1. And so what's the probability that y is less than 1? Well, that's going to be 0.5, because this curve is symmetric about 1. So on the left and on the right side of 1, we have the same area under the curve. And what's the probability that y is less than 0.5? That's going to be 0.125. So you can see that the probability that y is less than 1 is going to be 0.5. That is the area of this entire triangle. The probability that x is less than 0.5 would be this, 0.125. Okay, so I am going to stop the video here, and in the next two videos you will be looking at the you will see the uniform distribution again, an example on uniform distribution, and then you'll be looking at normal distributions. All right, so I will see you in the next two videos.